Hey everyone, today we're going to talk about a new cybersecurity attack you need to be aware of as an AI developer, a cybersecurity professional, or a business owner. Let's say you and your team spent lots of time, money, and resources to develop a state-of-the-art AI model. You put it out in the field, your customers are using it a lot, you're making lots of money, the customers are happy. This is great. Well, next week you see the news that your competitor has a new AI model that does almost exactly the same thing as your model. How is this possible? Well, this is possible through model extraction or a distillation attack. When you put your model out in the open, anybody can use it as long as they pay you. Maybe it's an API, maybe it's a website. You put it out in the open so customers can give you money. Well, nothing is to stop your competition or malicious hacker from setting up a company or themselves directly, sending lots and lots of input to your model, collecting that output, and now they have a pretty good idea of how your model works. So they can train a new model with the input data that it fed your model, paired with the output that your model gave, and they can create a model that acts almost exactly like your model. That is a distillation attack. Model extraction is very similar. They have access to the output of your model, but they also, through some means, were able to also get their hands on the training data that you use to create your model. This is a way for your competition or malicious actors to create a near identical copy of your model a lot cheaper, and they can avoid spending all the time, money, and resources that you spent to develop your own model. As you can see, this has big business and cybersecurity implications and something that you need to be aware of. In the next few minutes, I'll show you how to implement one of these attacks on Google Colab. All right, let's start off by doing some best practices and putting some information about our code up at the top. This way, anybody that comes, including ourselves, to look at our code later will be able to tell what this file is doing without spending a lot of time trying to decode what we wrote. All right, next we're going to put the import. I'm using Google Colab, so I have to do pip install for TensorFlow. If you're using a different environment, you might be able just to import TensorFlow. Let's run it, make sure everything downloads. All right, let's get our data that we're going to train and test our model in. We're going to use MNIST data. Again, this is a prototype model, and it's just an example. You could use other data sets to prove this. Then we're going to change the images. We're going to, first of all, partition them so we can make this training a little bit faster. I'm going to show what one of these images looks like. And then we need to reshape it in order that it can go into our input layer of our model later on. Same thing for our test images. Right there you can see that's on handwritten 5. That's what each of these images look like. Next, let's define our functions. That way we can automate this code and call it a little bit later, not have to write it out each time. I'm going to give it an optimizer and activation parameter. There are different ones that you could use. And again, we follow best practices. That way people know what these magic functions that we're writing do. And you can see as I'm typing that I'm using Google Colab, and it gives some code recommendations. Sometimes that's useful for saving time, sometimes not. As you can see, not all of these recommendations are exactly how we're going to do it. We're defining the different layers in our sequential model. Got a dense layer, a dropout layer, and then another dense layer. This is going to be our output layer. Let's fix the typos. Then we need to compile the model. We're going to use the optimizer that we feed to it, and then choose the loss function. All right, looks like it compiled. All right, next let's do our main section of code. We're going to instantiate our base model by calling that function we just wrote. I'm going to give it an atom optimizer and array lu activation parameter. Pretty standard. Again, if you're doing this attack, this is some of the things you will have to play around with and could make a little bit different in how well your model extraction or distillation attack works. I'm going to give it 10 epochs and give it validation data. Let's run that. Let's see what I do wrong. Oh, misspelled word. Here we go. There we go. We have our base model trained. So now we're going to create our extracted model. So we're going to get the predictions of the base model, just like we would do in real life. That would be the output of the input we gave to the model. I'll show you what this looks like. We'll pick one of them, and then it's not really human readable. So we're going to do this np-argmax, and you can see the label is 7. What it actually looks like is just a bunch of numbers. Those are different weights and parameters, but the biggest one is 7. So if we do that little bit of editing, you can see that we get a 7. All right, so we want to collect all of these and put them into a NumPy array so we can use that when we train the extracted model. We're going to train the extracted model on the output of the base model. You can see right there, we did that. Let's run this. It's going to take a little second as it goes through all the epochs. All right, there we go. So let's do another code. So now we want to see how our extracted model compares to our base model. If we were successful, it should look pretty much the same. So let's get the test images and test labels. We're going to use different data this time from the MNIST dataset to test to see how our extracted model compares in performance to the base model. Again, we got to reshape it. Yep, so let's get the accuracy and score of the base model as a baseline, giving it the test images and the test labels. Again, these are different test labels and test images than we did when we trained the original model. Let's do the same thing for the extracted model. Print this is the base model. Accuracy. Same thing for extracted model. Now we will also look to see what the layers of these models look like, to see if they're actually the same or not. Let's get the layers from the base model and from the extracted ones. All right, and then we're going to get the weights, and we're just going to select a random weight from the output layer and compare them to see what they look like. And I'm just going to put exclamation marks in between so we can tell where one starts and one ends. Oh, we got an error. So it looks like I did. I accidentally put 10,000 instead of 1,000. So I'm going to go back and change that. Same thing for this. I'm going to change it from 1,000 to 2,000. That's why some of our training epochs were taking so long. I'm going to rerun that code. You can see we got it working now. So you can see right here. All right, here we go. We got an accuracy that is pretty much identical. It's off by maybe point something percent, but it's pretty much the same output as the actual model. So you can see how this is an interesting way that you could get a model to have the same behavior as your competitor's model, something you need to be aware of as a developer or as a business owner. You can see that the actual weights there on the end don't actually look exactly the same as each other, but we have a model that pretty much has identical behavior. This is interesting from both an academic perspective and a business perspective. It's something to be aware of and to account for in your best business practices. Hope you enjoyed this code and presentation. Like us and subscribe if you'd like to see more videos like this.